So I talk about quantum gravity, time, and in particular quantum geometrodynamics, and I decided to organize this talk around some of the foundational questions you have put on the home page, right? So on the first two transparencies are just an introduction and then the question. So when talking about quantum gravity, of course the question is which approach to pursue. Yeah? John Wheeler already said that no question is more difficult than the question, what is the question? So basically, you can distinguish between approaches that directly quantize just gravity, quantum general relativity, or you go to more general frameworks such as string theory, also other approaches. So my topic here is quantum geometrodynamics, which is the oldest version of canonical quantum gravity. So what is quantum geometrodynamics? All approaches consist of have at their central equations constraints. H size is 0, and the oldest approach is the one which with the Wheeler-DeWitt equation. So what are its properties? Well, apart from the non-gravitational field, the psi depends only on the three-dimensional metric. Although, of course, it's invariant under coordinate transformation. The reason is actually very simple and straightforward. Just as in quantum mechanics, you do not longer have any trajectories. Trajectories here are space-time, and so if you just apply quantization rules, you don't have space-time anymore. You cannot parameterize it, so you don't have time. So it's a very conservative approach. But you then see that the Wheeler-DeWitt equation actually allows to introduce a sort of intrinsic time by its structure as a hyperbolic wave equation. It's also conservative in the sense that this equation gives the correct Einstein equation the semi-classical limit. That is, if you just ask for a wave equation that is behind the Einstein equation, this is what you get. Now the questions. Of course, they are not exhaustive. So the first one, are there reasons to believe that standard quantum mechanics is insufficient? I would say not from the point of view of quantum geometrodynamics, because so far it does not seem to lead to any inconsistencies. It just extrapolate the linear structure of quantum theory. Can we apply quantum mechanics to the entire universe? Yes, we can. It is even most natural to do so, I would say. As already DeWitt in his pioneering paper wrote that Everett's view of the world is a very natural one to adopt. In quantum gravity, where one is accustomed to speak without embarrassment of the wave function of the universe, it is possible that Everett's view is not only natural but essential. And if you look into the work on quantum cosmology, usually you do not modify the linear structure. What is quantum physics fundamentally about? I would say about reality, because if you make interference experiments, say nice experiments in Vienna about interfering biomolecules, they are about reality, not about information, whatever, and I would also view it in this context. Can one define probabilities? Well, the Wheeler-DeWitt equation is fundamentally timeless, and therefore you cannot accommodate probabilities in a natural way. However, you can do this, or try to do this in a semi-classical semi-classical von Oppenheimer type of limit where an approximate time parameter emerges. And that limit, the decoherence is very important. I shall say about this soon. In theories of inflation, which only makes sense in the semi-classical limit, one rule, however, may have to be replaced by another rule. The measure problem we had discussed during the workshop. On page, for example, argues that there are many such rules. So this is something that is not yet solved. This is a brief remark on decoherence. So decoherence, emergence of classical properties, is a crucial ingredient in interpreting quantum cosmology, because similar to the case with the sugar molecules, where you understand why you have, for example, chirality by interaction with the environment, you can also understand in quantum cosmology why you do not have all the interferences, why you really observe the classical space-time. For example, if you have a decoherence factor for our universe, our size, I mean, you can get numbers that are very, very small. On what side of the borderline between science and philosophy are parallel universes? I would say on the side of science. So I fully agree with Max's remark yesterday that if you have a theory, I mean, you should buy all of it and believe all of its consequences. Yeah, so we have a consistent framework, I think, and then you should view parallel universes in the sense of Everett also as real. Why did our universe begin in a low entropy state? I would say that at least in principle you can understand it, because there's a fundamental asymmetry of this equation with respect to intrinsic time. I mean, for the first time, we have this in a fundamental equation. So if you go to very early times, or we should say for small scale factor, alpha is the logarithm of the scale factor, this more or less becomes 0. So you have a very simple equation for small a complicated equation for large a, and if you have a very simple condition for small a, you automatically get an entanglement entropy. So at least in principle, you could understand, I would say, the error of time in this framework, and the expansion of the universe would even then be a tautology. Yeah, my last slide. Is there any hope of experimentally testing quantum gravity? I would say yes. After all, physics is an empirical science, and if there were no hope, I would not be interested in doing quantum gravity. But how? Well, maybe perhaps first through quantum gravitational corrections, like, I mean, with the Lamb shift as the first step towards understanding quantum electrodynamics. For example, in this framework, in the Oppenheimer approximation, you can have correction terms to the Schrödinger equation which go with 1 over Planck mass squared. Whether you can observe them in the near future or not, I cannot tell you, but certainly there is some hope concerning the observations of the Planck satellite. Thank you.